Any characteristic of a system is called a property. Some familiar properties of fluids are pressure, temperature, volume, mass, and so forth. The density of a substance is the mass of matter contained in a unit volume of the substance. Density can be illustrated by way of buoyancy, that is, observing which fluids sink or rise in other fluids. In this demonstration, cooking oil is poured on top of water, where it floats, since it's less dense than the water. Density differences in gases can be observed using the Schlieren optical method. Here, a turbulent plume rises from a cigarette lighter flame because the hot gas is less dense than the surrounding air. But the fuel inside the cigarette lighter is butane gas. It's heavier than air, and thus it falls. A small amount of liquid acetone in the bottom of this beaker produces a dense vapor that can be poured from the beaker almost as though it were liquid. In this computational fluid dynamics, or CFD simulation, cold air from an open freezer of the sort found in grocery stores falls to the floor. The density of a gas is inversely proportional to its temperature. Sometimes density differences can drive a fluid instability. Here, warm salty water overlies cool fresh water. Natural disturbances at the interface are amplified by the density difference, causing the two liquid layers to diffuse into one another, a phenomenon called salt fingers. A beaker of water at room temperature has a vapor pressure that's only a fraction of 1 atmosphere. However, when we heat the water, the vapor pressure increases. If we heat it enough, the vapor pressure reaches 1 atmosphere and the liquid boils. Some volatile fluids have vapor pressures much higher than that of water. This one, tetrafluoroethane, has a vapor pressure higher than 1 atmosphere at room temperature. It boils spontaneously without requiring a separate heat source. Water exerts great pressure on divers, and gases, especially nitrogen, become dissolved in the blood. If the diver ascends to the surface too fast, the high nitrogen vapor pressure causes bubbles to form in the bloodstream. The resulting medical condition, known as the bends, is potentially deadly. Vapor pressure is also an issue for high-speed propellers, because the local pressure around the fast-spinning blades can fall below the vapor pressure of the water. When that happens, a type of local boiling known as cavitation occurs. This high-speed movie shows cavitation in water flow around a blunt object. Cavitation can cause damage due to the effect of bubble formation and collapse near a surface. A CFD simulation shows that we can also model the formation of such turbulent cavitation zones. The specific heat of a fluid is the amount of energy required to raise the fluid temperature by 1 degree. Different fluids have different specific heats, and even a given gas has 2 different specific heats, depending on how the process is done. If the gas is confined to a fixed volume, the amount of energy required to raise its temperature 1 degree is called the specific heat at constant volume, C sub V. However, if we allow the gas to expand freely, then a somewhat larger specific heat at constant pressure, C sub P, is found. The difference is due to the amount of energy that went into expanding the gas. The ratio of these two specific heats, K, equal to C sub P over C sub V, is an important parameter describing the gas's thermodynamic behavior. Fluid compressibility describes the change in pressure required to produce a certain change in volume at constant temperature. Liquids are not very compressible, which is to say that their densities don't change very much, even over a tremendous pressure range. Gases, on the other hand, are very compressible. This is nicely illustrated by the Cartesian diver, a weighted medicine dropper filled with air, afloat inside a sealed bottle of water. When pressure is applied by squeezing the bottle, the water density doesn't change, but the air bubble inside the diver is compressed. As the air bubble shrinks, water comes in and the diver loses buoyancy and sinks. When we release the pressure, the air expands, drives the water out, and the diver's buoyancy is restored. This graphic little demonstration comes directly to us from that great 17th century French thinker René Descartes. And now, viscosity. We automatically think of a viscous fluid as thick, slow-moving, and sticky. But all fluids are viscous, including gases, and the faster you move through them, the more viscous drag resists this motion. Meteors enter the Earth's atmosphere at tremendous speeds and usually burn up due to the conversion of their kinetic energy into heat by the viscosity of the air. These burning rocks are erroneously known as shooting stars. We measure viscosity with a viscometer. One type of viscometer depends upon the wall friction inside a tube. Here, green-colored water drains faster than the more viscous blue-colored sugar water solution. The draining time can then be related directly to the liquid viscosity. Another type of viscometer generates and measures viscous stress in the fluid between a rotating rod and a surrounding cup. Temperature has a great effect on viscosity. For example, honey at room temperature is slow-flowing compared to water. If the honey is heated to about 40 degrees centigrade above room temperature, its viscosity falls and now it flows like water. Cool the honey to 15 degrees centigrade below room temperature, though, and it barely flows at all. Viscosity makes fluids stick to solid surfaces. Dip your finger in the honey and then withdraw it. The honey drains away, but right at the surface of your skin it has zero relative speed, so it sticks to your finger. This requirement of no relative fluid motion at a solid surface is known as the no-slip condition, and it comes directly from treating the fluid as a continuous substance. The no-slip condition is also vividly illustrated by this CFD animation, which shows colored velocity contours. The right side of the container of oil is moving upward, and viscosity causes the oil to be drawn up with it. In this case, the no-slip condition requires that the velocity of the oil in contact with the plate be the same as the velocity of the plate, which is colored red in this animation. A fluid with constant viscosity coefficient mu at any strain rate, represented by the velocity gradient du dy, is called a Newtonian fluid after Sir Isaac Newton. Water, air, and many familiar fluids behave according to this simple Newtonian law. However, some fluids, such as suspensions of particles or polymers, do not behave this way, and they're called non-Newtonian fluids. This thick solution of cornstarch in water is an example of a non-Newtonian shear thickening fluid. Hit it with a hammer, and it acts like a solid. Deform it more slowly with your finger, and it acts more like a liquid. Silly putty is a shear thickening memory fluid. You can bounce it around and it remembers its spherical shape. Let it sit for a while, though, and it spreads out like a viscous liquid. Other non-Newtonian fluids are shear thinning. It takes some effort to get them flowing. Ketchup is a famous example. You have to hit the bottle hard enough to exceed the ketchup's shear threshold, whereupon its viscosity falls and it begins to pour. Paint is another example of a shear thinning fluid. It's viscous enough to stick to the brush because the applied shear stress is small. But its viscosity drops dramatically as it's sheared, so we can apply it to a wall in a thin coating. Finally, there's the fluid property known as surface tension that makes a liquid surface behave like a stretched membrane. The water strider insect walks on water by making use of surface tension. He can even skim across the surface by surfing on the depressions made in the water by his legs. Observe the pinch-off of water droplets from a kitchen faucet in slow motion. Surface tension resists the breakup until the neck between the droplets breaks. Then it constricts the droplets into spheres, which contain the smallest surface area for a given volume. Here, surface tension effects are shown in a two-dimensional CFD simulation of liquid dripping from two holes in the bottom of a container. As the drops fall, surface tension tries to make them circular in shape, but viscous air drag tends to flatten them. As they strike an array of cylinders, the small drops coalesce into larger drops. When a drop of milk falls into a shallow pool, shown here in slow motion, surface tension resists the tendency to splash, but a spectacular splash happens nevertheless. This can also be simulated with CFD. Surface tension determines the contact angle of a liquid droplet on a solid surface. Here, water is dropped on a smooth plastic surface, producing a contact angle of about 90 degrees. Alcohol, dyed blue, wets the surface with a smaller angle, but a drop of mercury has a contact angle greater than 90 degrees. Mercury is non-wetting, and its surface tension is much greater than that of alcohol or water. Water in a glass tube wets the glass and thus curves upward at the solid-liquid interface, forming a meniscus. Mercury, however, does not wet the glass, and so forms a meniscus in the opposite direction. Water easily wets the surface of this bar of soap. Soaps and detergents are used to help wash things because they lower the surface tension of water, allowing it to soak into pores and soiled areas. Watch this soap boat demonstration. A drop of liquid soap at the stern of the boat breaks the surface tension there, and higher surface tension at the bow draws the boat forward. Here's a soap bubble being filled with a heavy gas. The surface tension in the liquid skin of the bubble constricts it and produces enough internal pressure to expel the gas back out the filling tube. The fountain of expelled gas is made visible by the Schlieren technique. As a final demonstration of fluid properties, observe these wine tears. Surface tension in the film of wine on the sides of the glass increases as the volatile alcohol evaporates, leaving water behind. This pumps wine up to the top of the film, where it collects and streams down continuously. This stately and beautiful phenomenon illustrates the two fluid properties of surface tension and vapor pressure.